Hello. So today we're going to be talking about the topological equivalence between real projective 3 space and SO3. So SO3 is the topological group of linear isometries that preserve orientation, aka the 3x3 orthogonal matrices with determinant equal to 1, as opposed to, say, O3, which is the orthogonal group on R3, for which the matrices could have determinant +1 or -1. But in this case, we preserve orientation, so it's 1. And then RP3 is the topological space defined as the quotient of the following partition map on S3, where we essentially identify antipodal points on S3. Yeah, cool.
So to make this proof work, we need to introduce some machinery, and the main piece of machinery that we need is quaternions. So for this proof, we're going to represent quaternions as a vector space of the complex matrices, 2x2 matrices over R4 with 4 basis elements, one being the identity matrix and the other 3, I, J, K, being defined as matrices below. And when we do this, it's really easy to show the relations between them. We can that we tend to know about the quaternions. We can just carry out the matrix multiplication and see all of these relations hold true.
So we also have some facts from the main source for our proof, which is Jean Gallier's book on geometry and computer science, particularly chapter 9. So first, all quaternions where the real part, or A, is equal to 0, are called pure quaternions. And this subset is isomorphic to R3 because we can just take the last 3 coefficients and consider them as a 3 vector. And then also pretty intuitively, the norm of each quaternion is the square root of a squared plus b squared plus c squared plus d squared, which is sort of what you'd expect.
And from Artin's algebra, we know that quaternions form a ring. And in fact, they're actually the first instance of a division ring. And by the distributive property, we also know that multiplication by a quaternion is bilinear. In addition, back to Gallier's paper, we know that we can represent left multiplication by a quaternion by a matrix vector product. And here we have it depicted. Right multiplication can be represented with, in a really similar way by inverting some of the elements in this matrix. And something really important to note about this is that the determinant of this matrix is a squared plus b squared plus c squared plus d squared quantity squared, which we will be using in the proof. Furthermore, just for some more definitions, we like the complex numbers, we have a notion of a conjugate of a quaternion, which is when we invert b, c, and d. And like the complex numbers, we can observe that a quaternion plus its conjugate is equal to twice its real part. So now we're going to begin the proof, and we're going to start with SU2. So SU2 is the set of 2x2 complex matrices where their Hermitian product is 1. So if you parameterize an SU2 by 2 complex numbers, we mandate that A bar plus B bar is equal to 1. And when we expand out A and B, we see that that the matrix looks very much like our quaternions. And when we expand A bar, B bar, we see that the relation between them is provides that these quaternions are in fact the unit quaternions. In addition, it's really it's easy to notice that because x1 squared plus x2 squared x3 squared plus x4 squared is equal to 1, we can define an isomorphism and topological equivalence to S3 because x1, x2, x3, x4 is the set of 4-dimensional points equidistant, radius 1 from the origin. So now we're going to discuss this conjugation action on the quaternions when with the quaternion you're conjugating by being non-zero, so we don't always get mapped to 0. And we're going to first recall that a quaternion plus its conjugate is twice its real part. And also with this conjugation map, it's easy to, when you do out the multiplication of the quaternions, to see that this map applied to the conjugate of a quaternion is the same as the map applied to the quaternion conjugated. And using these two facts, we can see that if X is pure, i.e. its real part is 0, which means that the quaternion, our pure quaternion plus its conjugate is equal to 0, we see that when we apply the map to this quaternion, because this map is linear and using the conjugate property we showed above, that the real part of the map applied to this pure quaternion is also pure, which means that this map preserves the pure quaternions. In addition to that, we also see that if we look at the matrix vector representation of this multiplication, if we think if Z, the vector, our conjugate quaternion, if this is a unit quaternion, by looking at the definition of this multiplication and its determinant, that being the a plus squared plus b squared plus c squared plus d squared quantity squared, we see that if this is a unit quaternion, the determinant is 1, which means that this transformation, and this is going to be true, but with the inverse multiplication as well, that this transformation is in fact an isometry. And since the determinant is 1, it's an orientation preserving isometry. And in addition to that, we can recall that quaternion multiplication is bilinear, which means that this map is also linear. So if it's 1 linear, 2 orientation preserving, 3 in isometry, and 4, it preserves pure quaternions, which we know is isomorphic to R3. We know that this is an element of SO3. And so we can actually use this map to construct a homomorphism from SU2 to SO3, where we take a quaternion and we send it to its conjugate map, which we have shown to be a member of SO3.
So in showing that phi is a quotient map, in fact, we first need to show that it's surjective, which means that given an element of SO3, we want to find a unit quaternion that matches. So we have this formula called Rodriguez's formula that induces an equivalence between 2 different representations of SO3, one being the 3×3 rotation matrix that we know and love, and the unique unit vector u hat and a positive angle theta if the rotation is not the identity. In the case that it is the identity, theta is 0 and u hat is any arbitrary vector. Right, so the formula is r equals I cosine theta plus 1 minus cosine theta times u hat transpose plus the cross product representation of u hat and times sine theta. And this essentially gives us a 2-way equivalence between these rotation matrices and the axis angle representation, as it's called. And we can further use another identity to find a unit quaternion from the axis and angle, and that's defined as z equals cosine theta over 2 in the real part, and then in the pure part, sine theta over 2 times the dot product of u and ijk. So that means, so then we can show that for all x in R3, the action of the rotation matrix on x is equivalent to applying the conjugation map to x using the unit quaternion that we found z. And this is all from course notes from Tomasi in 2013. So then we want to show some stuff about the quotient space of the conjugation homomorphism. And we observe that for all unit quaternions in SU2, phi of z is equivalent to phi of negative z, which just means that the opposite unit quaternion is actually the same rotation. And we already know that SU2 is equivalent to S3 because all unit quaternions are 4-dimensional real vectors, which are distance 1 from the origin. And we also know that phi is a quotient map because we've proven that it's surjective. So then by the quotient lemma, we have that SU2 with the partition of antipodal points, z and negative z, is equivalent to SO3. We also know that SU2 with this particular partition is equivalent to S3 with the same partition because SU2 and S3 are the same space. And then by definition, we know that RP3 is the same as S3 with this partition of identifying antipodal points. So then by this chain of homeomorphisms, we can say that the 2 spaces SO3 and RP3 are actually equivalent homeomorphically. So we now just want to talk about some visualization and application between the two. So we can sort of equivalently define RP3 as the following partition of the 3D disk, which is just S2 filled in, where essentially we identify antipodal points on the boundary and all other points are their own unique partition. So this allows us to visualize RP3. And then we wanted to figure out a way to interpolate between different rotations in SO3 to sort of translate between the two spaces. And so there's this clever thing called spherical linear interpolation, or SLIRP, which says that given two unit quaternions, we can find a path between them on the great circle in S3 using this fancy formula where omega is the subtended angle between the two. And then we can use this to interpolate between elements of SO3, thus allowing us to show an interpolation of different rotations, which corresponds to a path in RP3. So now we're going to show a demonstration. Okay. So you can see on the left, this is our representation of RP3, and the orange sphere is the boundary of the 3D disk. And then on the right, there's this bunny, which is showing us the rotation induced by the element of RP3 that we're currently examining in SO3, basically by rotating around the axis to the angle desired. And the important thing to note about this representation of RP3 is that the radius of the sphere depicted is pi. So when we have a point on the boundary of the 3D disk, we identify it with the antipodal point on the boundary. And what that means is that a rotation around an axis by pi and a rotation around the same axis by negative pi are actually equivalent, which we know from like trigonometry or geometry. So now the visualization. And you can see that as we get closer to the origin or to the boundary, we get to a 180-degree rotation. And once we get to the boundary, we have the identified points being shown. And then we rotate back on the opposite axis to the identity rotation, which is just represented as a zero-length vector from the origin. So the vector, the direction of the identity rotation doesn't actually matter because it's got zero length. So we just wanted to show sort of the connection between these two spaces using this little visualization. Thank you.
Thanks.